Welcome to this lesson on wave properties. Today, we'll explore three fundamental characteristics that describe all waves: amplitude, wavelength, and frequency. These properties help us understand how waves behave and how they transfer energy from one place to another. Before we dive into wave properties, let's understand what a wave actually is. A wave is a disturbance that transfers energy through matter or space without transferring the matter itself. Think about water waves in the ocean, sound waves traveling through air, or light waves that help us see. In each case, energy moves from one location to another, but the material itself doesn't travel with the wave. The water molecules, air particles, and space itself stay in place while the energy passes through. The first important wave property is amplitude. Amplitude is defined as the maximum displacement from the rest position. Imagine a wave moving along a string. The rest position is where the string would be if it were completely still. When the wave passes through, parts of the string move up and down. The amplitude is the distance from that rest position to the highest point the string reaches. This measurement tells us how much the wave disturbs the medium it's traveling through. Amplitude is directly related to the energy a wave carries. The larger the amplitude, the more energy the wave transports. We can observe this relationship in everyday life. A sound wave with large amplitude produces a loud sound, while a small amplitude creates a quiet sound. Similarly, a light wave with large amplitude appears bright, whereas a small amplitude results in dim light. The amplitude essentially tells us how powerful or intense a wave is. The second key property is wavelength, represented by the Greek letter lambda. Wavelength is the distance between two consecutive identical points on a wave. For example, you can measure the distance from one crest to the next crest, or from one trough to the next trough. This distance remains constant as the wave travels through a uniform medium. Wavelength is measured in meters and varies greatly depending on the type of wave. Radio waves can have wavelengths of several meters, while visible light has wavelengths measured in nanometers. The third essential property is frequency, represented by the letter F. Frequency tells us the number of complete waves that pass a fixed point per second. It's measured in a unit called hertz, abbreviated as Hz. 1 hertz equals 1 wave per second. If 10 waves pass a point in 1 second, the frequency is 10 hertz. Frequency describes how rapidly the wave oscillates or vibrates. Frequency has real-world effects we experience daily. In sound waves, high frequency produces high-pitched sounds, like a whistle or a bird chirping. This means many waves are passing per second. Low frequency creates low-pitched sounds, like a bass drum or thunder, where fewer waves pass per second. The human ear can detect frequencies ranging from about 20 Hz to 20,000 Hz. Different frequencies give us the rich variety of sounds we hear in our environment. Finally, let's look at the key relationship connecting wave properties. The wave equation states that wave speed equals frequency multiplied by wavelength. In symbols, V equals F times lambda. Here, V represents the wave speed in meters per second, F is the frequency in hertz, and lambda is the wavelength in meters. This fundamental equation shows us that if we know any two of these values, we can calculate the third. It reveals the interconnected nature of wave properties and helps us solve practical problems involving waves.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.